So there are in this video we're going to look at cubic spline examples. So the question is, construct a natural cubic spline that passes through the points 1, 2, 2, 3, and 3, 5. Now there are two regions here. The number x, our x points, data points belong to 1, 2, okay, and the other one is of course 2 to 3, okay. Within 1, 2 we have the polynomial s0 of x equals. So we have that, and you'll see that this point here, this number here, 1, x minus 1 squared, x minus 1, x minus 1, x minus 1 squared, and cubed, this 1 comes from this, the first point in the interval. So now the next one is of course s1 of x, and that's equal to a1 plus b1 into, similarly, the first point in this is 2 here, so this will be x minus 2, this second polynomial. So your first step will always be split the regions, and for each region you see here there will be a polynomial. So there's 2 polynomials in this case. 3 points means there will be 2 polynomials, 2 splines. So next, our next objective is going to be to look for these eight unknowns. So we have 8 unknowns to find. 8 unknowns. So we have to find 8 unknowns. To start with, we'll use the point 1, 2. So s0 of 1 should be equal to 2, which means as we substitute the point 1 into s0, you will see here that this will go to 0, this will go to 0, and this will go to 0. And all it will leave is the a0, so a0 equals 2. So we have one of the points, and so we have 7 more to go. So we found one of these. Okay. Similarly, we'll go to the next point. So s0 of 2, in fact, is equal to. So now we have to, let me just clarify something here. You see these 2 points here, 1, 2, and 2, 3. Okay, both are in this region from 1 to 2, okay, and these 2 points, well, this is an overlap, and this point are both in this other region 2, 3. So the 2, 3 point here, this one here that you see, is overlapping. This is where the matching condition also will apply. So anyway, s0 of 2 should be 3 according to the data, so that means we'll end up with. So what's going on here, just to show you, so what I've done is basically I'm substituting this 2 into here. So 2 minus 1, 2 minus 1, 2 minus 1, all these are 1s. So you end up with a0 plus b0, c0, d0. Now a0 we already have, so I'm going to replace that. Okay, and I'm going to put in, sorry, just 1 second. I'm going to put in, instead of a0, we'll substitute the 2. But anyway, this should be equal to 3. And this implies that we end up. So we end up with b0 plus c0 plus d0 equals 1, because put in the value of a0 is 2, so we end up with this, and we label this as equation 1. Now we'll go to the next one, which is the second polynomial. So let's use the other 2 data points. So we'll use now s1 of 2, and that's equal to 3 as well. Remember, that also is the matching condition. So s1 of 2 means that when we substitute that in, we end up with a1 equals 3, because when the 2 goes in, this will be 0, 0, and 0, so they'll all disappear. Just leave this a1 alone, so a1 should be equal to 3. So let's put a box around that. Now we have, in fact, 6 unknowns to find still, and so far we've got 1 equation. So let's move further on. S1 of the other and last point now is 3, and it should be equal to 5. And S1 of 3 equals 5 means when we substitute that in, we end up with. So we'll end up with this, and we take the 3 across to the other side, so we end up with this equation, b1 plus c1 plus d1 equals 2. So we label that as our second equation. Now we'll start using the matching second matching condition, which is on the first derivative. So let's do that. So s0 dash of x, let's compute that. S0 dash of x is going to be so So the first derivative of S0 turns out to be this, B0 plus 2C0 into x minus 1 plus 3D0 into x minus 1 squared. Similarly, S1 prime turns out to be this. Okay, so let's move on. So the matching condition S0 dash of 2 should equal S1 dash of 2. This implies that we will have the situation when we substitute the 2 into the first one here, the S0 derivative, we end up with B0 plus 200 plus 3D0, and that should be equal to, when we substitute the 2 into the second, this equation that you see here, the S1 prime, everything turns to 0 except B1. So we have this, and this turns out to be the equation, so we'll label this as equation 3. The other matching condition, remember, is same thing, only with the second derivative. Now, in order to do that, this implies, of course, that the second derivative of S0 turns out to be 2C0 plus 6D0 into x minus 1. Okay, and this one, S1 double prime of x, turns out to be, of course, 2C1 plus 6d1 into x minus 2. So now when we substitute into the first of these, the number 2 for x, we end up with, this implies that we get 2c0, okay, plus 6d0 equals, and in the other one we'll put the 2 in, remember, so that will give us equals 2c1. So that is equation 4. All right, now let's move on. Now we have applied all the matching conditions, so now the only thing that remains is to apply the boundary condition. So the boundary condition BC here, just short, S0 double prime of the first of the one of the endpoints, the starting point, which is 1, should be equal to 0, and of course the other one will be that S1, because the other point is 3, remember, the other endpoint, so that is for this polynomial, S1 double prime of 3, and that should be also equal to 0. So these are the boundary conditions. Now these conditions will imply, the first one of these implies that S0 double prime of 1, so if I substitute the 1 in here, you'll see that'll go away and leave you with the 2C0, so that means that C0 equals 0. So we found yet another one of the unknowns, so we still have now we've got 5 to go. Okay, 5 to go. Anyway, this condition here implies that in the second, this expression here, the second derivative, we put in 3 instead of x, so 3 minus 2 is 1, so 2c1 plus 6d1 equals 0. And we'll label this as equation 5. So if you see now, we've got 5 unknowns and we've got 5 equations. Now let's update and collect these together with the value of C0 also, updating the equations, and let's summarize the equations below. Or next. Sorry, let's summarize the equations next. So this is the summary of the equations. As you can see here, we've got the 5 equations and we've got 5 unknowns. Now I'm not going to show you the full solution, but I can show you how you can proceed. And the one way to do this is, of course, the best way to do this is to go by solving this as a system of linear equations, and that means you need to order your unknowns first. And the order we have here is as follows. So we have basically got this order: B0, D0, okay, and then B1, C1, D1, and our right hand side. So accordingly, we'll end up with this system. Let me just show you here quickly. So you'll have 1, 1, and then 0, 0, 0, the first equation, and then 1. And the second equation will be 0, 0, 1, 1, 1, 2. And then the third equation will be 1, 3, B0, D0, and minus B1, so minus 1, 0, 0, 0. This equation here, so that's this one done, this one done. This will be 3d0 minus c1, so 0, 3, and the last one will be, wait, excuse me, sorry. Yeah, no, it's okay. Right, let's finish this off. So the last one, which is this one, 2c1, so 0, b0, okay, 0, and then 0 here as well, 2, 6, 0. So there you have your augmented matrix, and you can use something as simple as Gaussian elimination to solve this, and when you do, we get this result. This implies that b0, it turns out to be equal to 3 over 4, okay, and d0 is going to be 1/4, okay, and b1 is 3 over 2, and then we have c1, so c1 is going to be 3 over 4, and d1, the last one here, is going to be minus 1/4. So these are the values. Now, how we write the final is as follows. So we have 2, so this will be the first polynomial, remember. Now let me bring back here, remember a0, we already have these, so just to remind you, let's go back here. There's a0 is 2 and a1 is 3, and remember c0 is 0, okay, so a0, 2, and 3. So a0 is 2, pardon me, just one second. So a0 is 2, a1 is 3, and c0 is 0. So now we've got 1, 2, 3, 4, 5, 6, 7, 8 of our unknowns. So now as we put these together, remember the first polynomial is the with the 0 subscripts. So a0 is 2, b0 is 3 over 4, so plus 3 over 4 into x minus 1, okay, and then c0 is 0, so nothing there, and d0 is 1/4, so you'll get plus 1/4 into x minus 1 cubed, and this is for, of course, x in the first region, or the first region, yeah, 1, 2. And then the next polynomial is going to be the subscript 1s. So a1 is 3, plus b1 is 3 over 2 into x minus 2, plus c1 is 3 over 4 into x minus 2 squared, plus d1 is negative 1/4 into x minus 2 cubed, and this is for x in the region 2 to 3. So that completes our cubic spline interpolation for the 3 data points. So just as an added example, just to show you that we used we found the natural cubic spline in this example, which you see above there. Now if we want to do the same problem but find the clamped cubic spline, remember all the conditions will be the same, except, let me just go back here very quickly, and you saw this condition here. This is the condition that will change. Everything above, all of these conditions and everything, all of the equations, everything is fine up to this equation, up to 4. Everything is good, but these 2 conditions now will be replaced by other conditions. So if we were to do that, let's therefore look at trying to continue this with these 2 conditions changed, and let's see what happens. So let's see what happens. So let's do that. Let me just say something else here important. In order to solve this problem, first of all, you would have to be given this condition that S1 dash, that S dash of 1 is equal to 2, and S dash at the other endpoint 3 is equal to 1. So these have to be given to you in the question. Okay, so given these conditions, this means that S0 dash of 1 should be 2, and of course S1 dash of 3 should be equal to 1. So these are the 2 additional conditions And then when we apply these conditions to our polynomial, if we go back here, see here, this is where we are now. This is our S0 and S1. This is here. You'll see S0 dash is this one and S1 dash is this one. So we are applying S0 dash of 1, which means all of these will disappear and leave you just with the B0 here. Okay, so that will mean that B0 is 2 and S1 prime of 3 is going to give us an equation. So let's have a look at what results. So let's just do that, and if we do, we end up with this condition tells us that clearly B0 is equal to 2 and S1 3 dash is equal to 3 gives us this equation that 1 plus 2C1 plus 3D1 is equal to 1. So we get this equation. So now if we were to summarize our equations, I've just written them here again for you. A0 is 2. So all of these equations, now we need to update them with B0 equals 2. So if we do that in here, so if I can, so this equation, this will be changed and this will become C0 plus D0 equals, the B0 is 2 goes the other side, gives us minus 1. Okay, and this equation, of course, will also need to be updated, and it will be 2C0 plus 3D0 minus B1 equals, we'll take the 2 to the other side, so it's minus 2. So that becomes minus 2. So that one's updated. And now we have this system of equations, which when we solve, in fact, like I said in the previous example, as we solve it, we end up with the following result: s of x turns out to be this time equal to. You can see here, this is the resulting polynomial, and what I want to do is just show you both here, so you can see the difference between these two. Here you'll see that 2, 3 same, 2, 3 same, 3, 4 has changed. As you can see, this was 2, this 3 over 2 is the same, this 1/4 has become minus 5 over 2. This is different as well, and you can see there's a cubic appearing here, and there. Here the square was missing, now it's appearing here, and so on. So anyway, you can see the clamped condition gives you a different polynomial fit or cubic spline. So now this brings us to the end of this example. So we've looked at two examples, one with the same 3 data points, natural cubic spline and clamped cubic splines. We'll stop here.